Swayam Prabha. Digital India. Educated India.
Hello everyone. Welcome to yet another session of our NPTEL on nonlinear and adaptive control. We are into the second week of this course. I am Shrikant Sukumar from Systems and Control, IIT Bombay. As always, we have our nice motivational image right in front of us, which is a rover on Mars. And these are the sort of autonomous systems that we hope to drive with algorithms that are developed through the course of what we learn this semester. All right. So, without delaying any further, let me go into the course material. So, if you remember, last time what we had done was the first thing was that we discussed this corollary of the Babolat's lemma, the very famous Babolat's lemma. And we also, of course, have an exercise which requires you to prove the corollary in some sense, okay, using the original lemma itself. Then we started to look at how we can use Babolat's lemma in convergence analysis in typical adaptive systems. Okay, and in order to do that, we had this nice setup where we have a spring mass damper system which is moving on the horizontal plane, and we very quickly derived Newton's law, second law based equation of motion for this system. And we of course get a dynamical system of the form 3.1, which is reduced to the state space form in equation 3.2. After that, we constructed these error variables, right? So the aim in most of what we do is to drive systems towards some optimal or some nicely behaved trajectories which we are predefined in some sense. Okay. One of the things I forgot to mention are that typically these trajectories are assumed to be C infinity, that is infinitely continuously differentiable. And of course, separately from C infinity, these signals are also assumed to be bounded. Okay, bounded with bounded derivatives. Okay, so these are standard assumptions that we make on all desired trajectories that we choose to work with. Okay, otherwise, your system gets driven to infinity and things like that, which is something we want to avoid. Okay, so once we had these desired trajectories, we defined our error variables using these desired trajectories. Yeah, and then after that, we computed the dynamics of these error variables. Okay. Now, in order to do control design, what we did last time was to create a target system. Now, the idea behind the target system is to have a stable system, asymptotically stable at least, because we want these errors to go to zero, right? So we wanted to create this asymptotically stable system. In this case, of course, exponentially stable because it is linear, right? So we create this target system which is sort of compatible with the original system, yeah, and in the sense that in the original system also we had E1 dot equals to E2, right? And so we have the same in the target system. However, the second piece of the dynamics which contained the control in the original system was prescribed to be a nice negative terms, right? And we could, of course, prove that this is in fact an exponentially stable system just by using root locus, sorry, route Hurwitz, yeah, even root locus, and um, typical eigenvalue computations. Yeah, and once we understand that this is in fact exponentially stable, we want this original system to follow this target system. In order to do that, we compute a control law f of m of this form. Yeah, and given this 3.5, that is, if this 3.5 gets plugged here, you are going to get this target system 3.6. All right. So this is where we were last time. Now this is equation 3.6 is what is called the closed loop aerodynamics. Why is it closed loop? Because we have closed the loop using the control. Yeah, this is very standard terminology in control theory. What's the idea? The idea is that um, the control depends on the states themselves, right? So these terms are all state dependent terms, right? Therefore, you need some kind of a feedback from the system, right? So that's why these are called feedback controllers. So you need a feedback from the system. That is, you need some sensors mounted on the system, right? Which will give me this information. Yeah, without any sensor mounted on the system, it is impossible to actually implement 3.5. Okay, and then what do? We take the information from the system and feed it back into the system via some kind of a control loop. Yeah, via some kind of a control loop, and hence this is called closing the loop. Yeah, take information from the system, process it in a controller, and send it back into the system as a new control signal or an actuation command. In this case, as you can see, the control signal is simply this f of t, this kind of a force that I have the ability to exert on this Mars. Yeah, excellent. Now that we understand this, now that we understand this quite well, so this we that's why this is called closed loop aerodynamics. Right? This is called the closed loop aerodynamics, and these are the quantities, that is E1 and E2 are the quantities that we want to drive to zero. Now, what do we want to do? We talked about this last time, right? So let me actually label our lecture. So this is lecture 3 of week 2. Okay, so we did talk about this last time. What we want to do is we want to prove that this system is in fact uh, asymptotically stable, yeah, using potential functions. Why did we say we were interested in doing it? Because it's obvious that in this case we have other tools like your eigenvalue analysis, your Routh-Hurwitz criteria. You have so many methods to in fact conclude exponential convergence. Why do we need potential functions? The point is, in a lot of cases, our target system, turns out to be nonlinear. Yeah, you may have to make your target system nonlinear. You have no choice. Yeah, and if that happens to be the case, then you are forced to use some kind of a potential function analysis, because in those cases your eigenvalue analysis or your Routh-Hurwitz is not possible. They are all tools that can be used only for linear systems. Okay, and since that is the case, we of course want to see what to do in the more general scenario, how to do potential function analysis for convergence in the more general scenario. Okay, so notice that Barbalat's lemma is only a tool for proving asymptotic convergence. Okay, we already looked at this distinction, right? Well, I'm sorry, we have not yet looked at this distinction, but we will very soon. So don't worry if you're confused. The idea is that Barbalat's lemma proves only convergence. Yeah, that is it. That is, it will show that it claims, as you can remind yourself from the theorem, that some function goes to zero as t goes to infinity. It doesn't say anything about what happens before infinity. It might very well be the case that the function goes to infinity, explodes, and then comes back and converges to zero as t goes to infinity. Yeah, so you could have something like this. Yeah. So, I mean, just like I said, I mean, you could essentially have something funny happening with the function. Yeah, you could have something funny happening to the function like this before infinity. Okay, and this is not really predicted by the Babolat's lemma. Okay, it is not predicted by the Babolat's lemma. So I want you to remember that Babolat's lemma only helps you prove asymptotic convergence. That is, it talks to you, it tells you something about the behavior as time grows large. Yeah, excellent. Excellent. So once we understand that, let's try to see what we want to do. So what we want to do is we want to prove asymptotic convergence, like I just said, which is mathematically defined as limit as t goes to infinity e1 of t and limit as t goes to infinity e2 of t has to go to 0. Right? So this is important. Okay, so this is what you have. Limit as t goes to infinity e1 of t and limit as t goes to infinity e2 of t. Both of these will go to 0 as t goes to infinity. Okay, so what we do, as we had planned, we use an energy functional or we use a potential function, whatever you want to call it. Yeah, and what is this? This is very standard for spring mass dampers. This is v of t is uh, half k1 e1 square plus half e2 squared. Okay, so these are of course functions of time, right? It should be obvious to you that this is non-negative, that is, it is lower bounded by 0. Why? Because I'm simply taking squares of quantities, right? So it's obviously lower bounded, no problem. Excellent. So now that we understand that this function is lower bounded, right? What do? We take the derivative of this function. We very carefully take the derivative of this function. So let me repeat what the function was. It was v is I'm sort of ignoring avoiding writing the time argument here. V is k1 e1 square half plus half e2 squared. Okay, and then we simply take the derivative, which is k1 e1 dot and e2 dot. The 2's cancel out because of the 2 in the derivative. Okay, and what do I do here? Here now I substitute from the dynamics of e1 and e2. Yeah, I substitute from the dynamics of e1 and e2. Yeah, and what is this dynamics? It's already written here, right? This is my closed loop aerodynamics. Yeah. Notice we have assumed all the parameters are known and therefore we can actually reach here without having any issues. Yeah, if these parameters were not known, this is not possible. Okay, but we will worry about that later. Yeah, that is where adaptive control will go. Excellent. So I substitute for e1 dot as e2 and e2 dot as minus k1 e1 minus k2 e2. Okay, and then it should be very clear to you that by virtue of the construction, I did something neat in the construction, right? Which may not have been obvious to you. Why did you do that? Yeah. So what is that? I put a scaling k1 e1 squared. Okay, and because of the scaling, I get a k1 e1 e2 here, right? And here, of course, I already have a minus k1 e1 e2. Yeah, and so what happens is that these two terms, of course, cancel out. Yeah, by virtue of my smart construction. If I did not do this, and this is where some kind of an experience or intuition, good intuition in constructing Lyapunov functions or these potential functions comes into play. Yeah. So because of my smart choice of V, yeah. By the way, it's not my smart choice. This choice of potential function for spring mass damper has existed forever. Yeah, so I'm just calling it my smart choice just to tell you that if you are dealt a new problem, which is not a spring mass damper, which is something more unusual, then you will have to make a smart choice. Okay, excellent. So yeah, so due to this rather nice choice of V, yeah, what happens? We get cancellation of these two guys here. Okay, and then I'm left with minus k2 e2 squared. Okay, excellent, great. Um, and then what do I have? This is essentially obvious that v dot is now less than or equal to 0. It can never be positive, right? Because again I have a square term with a negative term, and k2 is of course a positive quantity, right? So k2 is obviously positive, right? Both k1 and k2 are positive quantities. Okay, great. So I know that v dot is less than or equal to 0. Okay, so what do we want to do? We are now claiming that as t goes to infinity, both E1 and E2 will go to 0. Okay, this is our claim. And of course, we want to see how to prove this claim. Yeah, and this is where our Bablat's lemma will come to the fore. So the analysis that we do subsequently is called the signal chasing analysis. Yeah, we chase through a lot of signals. Yeah, and this has very, very standard steps. Okay, so the important thing for all of you who are taking this course is to almost memorize these steps, because every time we try to use Babolat's lemma, these will be the standard steps that need to be implemented. Okay, so every time these will be the standard steps. So I want all of you to sort of memorize almost, what these steps are. Okay, excellent, excellent. So let's see. So the first step is to note that V is bounded. Okay, what does it mean? It means that V is lower bounded. Yeah, we already said that because it's composed of squares, so it's a non-negative quantity, so it's lower bounded by 0. That's obvious. And further, it is not increasing. Why is it not increasing? Because the derivative is less than equal to 0. Yeah, you know very well that for any function of time, for example, if the derivative is less than equal to 0, then the function cannot increase. It can stay constant or go down. Yeah, the function is lower bounded and non-increasing. And this immediately lets us use lemma 1.1. What was lemma 1.1? This is one of the first lemmas we did. It said that if a function is bounded and non-increasing, and so then the function has a finite limit as t goes to infinity. Then the function has a finite limit as t goes to infinity. Okay, and that's what we use, lemma 1.1. Yeah, that's was the use of all these very, very nice lemmas. Okay, so since v is lower bounded and it is non-increasing, using lemma 1 we have that there exists a finite limit. Yeah, so v infinity, let's call it v infinity. We are calling it v infinity. Okay, excellent. The second point is that both E1 and E2 are bounded. Why? Because again, v dot is less than equal to 0, and this implies that Vt for any time t greater than equal to 0 is less than equal to 0. Okay, obvious again. Yeah, because it's a function of time, derivative is negative. It's nice and continuous also, differentiable and everything because of how it's constructed. Yeah, and therefore, whenever you have, you know, uh, the derivative to be less than 0, less than or equal to 0, then v of t has to be less than equal to v0. What does it mean? It means that v itself is bounded, because whatever value I started it at, it's always going to remain below that value. Okay, so v is bounded. And now notice that v is composed of quadratics in e1, e's. That is, v is actually e1 square and e2 square. So it should be obvious to you that if v is bounded, then all of these have to be bounded. Yeah, because there's no subtraction happening anywhere. It's easy to argue. If E1 was unbounded, then V will become unbounded. Or if E2 is unbounded, V will again become unbounded. So the only way for V to remain bounded is that both E1 and E2 remain bounded. Okay, this is rather critical. Yeah. So if V is bounded, both E1 and E2 are bounded. Okay. Purely because of a quadratic nice construction, yeah, which is squares, they're all getting added, nothing is getting subtracted, right? Instead, if V was of the form something ridiculous like E1 minus E2 square, and I said V is bounded is same as L infinity. Remember, I cannot guarantee E1, E2 not necessarily bounded. I cannot guarantee that they're bounded. Why? Because if E1 can become really large and E2 can become really large, but they can remain same. Yeah, they can go to infinity together, but this difference will always remain bounded. Okay, so if this, so this is sort of a counter example. Remember, yeah, yeah. So V bounded uh, implies E1, E2 bounded because of nice construction of V. Okay, if I make some arbitrary and what I would call ridiculous choices for V, this will not be true. So always be very careful whenever you claim, it's not that I just wrote a V, therefore if V is bounded, even E2 are going to be bounded. No, it's not a guarantee. Yeah, and I gave you a counter example. If I choose V as E1 minus E2 square, yeah, this still is greater than equal to 0. Remember, this still has a lower bound. Yeah, but V being bounded in this case will not imply that the errors are bounded. Okay, excellent. Right. So and of course we are using boundedness and L infinity interchangeably. We have already proved this in class that L infinity is same as boundedness of the function. Excellent. The next and a rather critical step is that E2 is an L2 function. Yeah. So we are coming back to everything we have learned until now of these signal norms and everything, function norms, vector norms, signal norms. Yeah. So keep these definitions in your mind. Yeah. So we are claiming that E2 is an L2 function. How do we claim that? So what do? We integrate V dot from 0 to infinity. Okay. So this is where we integrate both sides. Okay. Now I know, so the right hand side is of course minus k2, 0 to infinity, e2 squared t dt. Okay. Now from the left hand side, I know is just, this becomes, if you may, this is just dv dt. So this just cancels out. So this just becomes an integral of dv. And so that is simply v at infinity minus v0. Yeah. Now, amazing thing. This can be evaluated only because we have step 1. Okay. If v infinity was not defined or if it was not finite, this cannot be evaluated. Okay. So great. So because of the step 1, I can make this evaluation on the left hand side. It's v infinity minus v0. The right hand side I don't touch. I don't do anything to the right hand side. It is simply e2 squared dt. Now what? What do I know? I know that L2 norm of this E2 signal is actually this guy. Is exactly this guy. Yeah, because it's a scalar quantity. I can put an absolute value, but it is irrelevant. It is irrelevant. I don't have to. Okay, that should be clear to you. Excellent. So now that I know this, right? So this is my 2 norm of E2. So what do we know now? That this is the 2 norm of E2. What do we have essentially? And this quantity here is what you have here. Okay. So from 312 and 313, what can I say? I can say that the V infinity minus V0 is nothing but minus K2 times square of the 2 norm. Okay. And I also know V infinity minus V0 is bounded, because V infinity is a finite quantity, V0 is a finite constant, because I initialized it at a finite quantity, and it would be ridiculous otherwise. And of course, so what do I have here? From here I have the norm E2, the 2 norm of E2 is actually square root of V0 minus V infinity divided by 2. Now notice very carefully that this guy on the top, yeah, so this quantity on the top, that is this guy, is in fact greater than equal to 0. So we don't have to worry about imaginary numbers coming out of this. This is greater than equal to 0. Why? Because V is a non-increasing function by our step number 2. Yeah, V is non-increasing, right? We just said it here. Therefore, V infinity, which is the value of V when t becomes really large, has to be less than equal to its value when time is 0. Therefore, this is non-negative, so you have a non-imaginary outcome here. So it's a sanity check. Okay, excellent. So what do we have? Because of this expression, I know that this right-hand side is finite, and this is precisely what it means for the signal to be an L2 signal. It's precisely what it means for a signal to be an L2 signal, and therefore we say that as per our definition, E2 is an L2 signal. Excellent. So I want to go ahead and summarize, what we did today. Yeah, we will continue, of course, with more of our discussion next time. What we looked at today is we started off our analysis, our signal chasing analysis. Yeah, uh, we saw that Babolat's lemma can only prove asymptotic convergence and cannot tell us anything about the behavior of the function as for times which are less than infinity. So nothing about the transients, only about the steady state. Yeah, in typical first level control systems language. Yeah. And then we looked at what is asymptotic convergence, and then we saw a few steps of the signal chasing analysis. Yeah, this analysis in which we prove signals go to 0 is called a signal chasing analysis. In order to do this, we chose a very nice, very smart potential function. Yeah, and this helped us to show that V is strictly greater than equal to 0 and V is non-increasing. And this is where we started our analysis. Okay, and this is how we started with proving a few of the steps of the signal chasing analysis. What we will do next time is, of course, complete at least one step of one piece of the signal chasing analysis, and we will see how far we get into the rest of the proof of asymptotic convergence for signals E1 and E2. Okay, so the important things to remember here are the very, very nice, smart choice of potential function was critical. Yeah, we saw that an unusual choice would not let you prove your asymptotic convergence as you require. Yeah, and this is rather critical thing to remember. And the other thing to remember is that all our knowledge of our all these L2 functions, LP spaces, L infinity spaces, boundedness, norms, and all the lemmas that we learned, they start to get used here. Yeah, and these sequence of steps we do remains almost identical for the entire course whenever we do Babolat's lemma based analysis, and this is why it is rather critical that we almost memorize this set of steps. Okay, so I would strongly urge you to commit to memory these set of steps that we do, because they remain more or less identical. I mean, of course, the expressions are different, the steps themselves remain identical. All right. Okay, this is where we stop today. Thank you very much.